record on this.
Amazing. Okay, awesome. Thanks, Ed. Okay.
My mic's still on. It's not me.
Ben?
All right. Okay, so my name is Robert. Thank you for inviting me. I'm going to talk today. I've got a hot take on CVE 2024-3094, which we have been calling the xz-utils backdoor, but I think that is a bad name. This is not the xz-utils did nothing wrong, so I'm here to vindicate xz-utils. And I'm going to point all the blame on GNU IFUNC. Has anybody ever heard of GNU IFUNC? Nobody. That's why it's not getting any attention, right? Because we've never heard of it. So this, like, the real culprit is hiding, and I want to shine the spotlight of justice on this garbage ass software. So, okay, so this was a backdoor. Yeah, again, first off, don't call it that. This is the SSH thing from March, not the SSH thing from July. Totally different thing, right? And if we stop using computers, we won't have to worry about this stuff. So what happened is an attacker put some malicious code into the xz-utils repo, but that's not really where the problem starts. Systemd, everybody's favorite init system, depends on xz-utils. That's been happening for a long time. xz-utils does compression. A lot of people depend on it, right? On Debian and Fedora, SSH is modified to depend on systemd. This is because you know how you can restart SSH even while you're logged into a remote host, right? So when SSH restarts, it does a lot of shit that like normal apps don't need to do, right? What else needs to maintain an administrative connection to itself while it's rebooting? So because it like restarts in a weird way, systemd used to lose track of it. And so systemd would be like, SSH isn't running, but it would be up and running. So the solution was not to make systemd smarter, but to make OpenSSH use libsystemd to like notify. So there's this thing called SD notify that a lot of folks use to like tell systemd like I'm restarting, I've come up, whatever your server status is, right? So the malicious code in xz-utils loaded an attacker's public key into OpenSSH because when SSH depends on systemd, systemd depends on xz-utils. xz-utils is now in the same address space as OpenSSH. So that's sort of the heart of the problem here. And if it was not for Andres Freund, all of these hosts that run like this in the world, which is a lot of them, would have been compromised. So I think we should all take a moment to celebrate Andres. He really did a global service. Okay, so now I want to talk about what iFunc'd is. It is a weird GCC feature. It allows your program to modify itself at runtime. Now, a lot of dynamic languages do this, like Python. You can modify Python programs at runtime. That's no big deal. These are C programs that can modify like the text section of the program while it's running. That's fucking stupid. Because it also allows an attacker to modify your program at runtime. So let's talk about how this sort of works. The idea is that you can pick an implementation of a function at runtime. So I've got this program that will greet users. The idea is that I want to give a polite greeting on Tuesdays, because Tuesday's Lopsa Day. And if it's not Lopsa Day, I want to give a mean greeting. So it calls, in main, I call this function greet. Greet's not a real function. It is an indirect function or an iFunc'd. So what happens is the first time we call greet, it checks the day. If it's Tuesday, it returns a function pointer to polite. If it's not, it returns function pointer to mean. So on Tuesday, I want to be polite, and on otherwise, I want to be mean, right? So when that greet function returns mean, what happens is when the rest of the program calls a greet, the mean function is what actually will be run. The result is stored, so you only have to, this iFunc'd is called a resolver, this thing that makes a decision about what the real function is. That only has to be called once. If you had to call that every time, it might be expensive, it might not. But those results are stored, and that's a silly example. where people actually use this, where libc uses it because nobody else does, is for performance optimizations. So you can check your CPU features. So like, right, like Celerons don't have like vector instructions and stuff, and your Xeons, or reason they cost a lot of money is because they've got all these extra features. It's not just the cache, there's actual instructions that are on the Xeon that are not on the cheaper CPUs, right? So you can query dynamically for CPU features, and you can use a different algorithm depending on what the CPU can support. So let's say I've got AVX2. Everything has that now. It's an older one, right? But let's say I want to check to see if I have that, then I can use maybe an algorithm that's optimized with AVX2 instructions. If I don't, then I can fall back to some generic code that I know, like, okay, this doesn't use any special instructions. This will work everywhere. But if I've got AVX2, I want to use the faster. So yeah, so I can simultaneously optimize the same binary for different sort of like, subcategories of processor. So this is slick because I can just ship one thing and then it will detect the CPU features and sort of like reassemble itself dynamically. And that's why people like it, because as a programmer, you're like, oh, this is very elegant. This is very abstract, right? But as a security person, you're like, the binary is rewriting itself after it's loaded into memory. That's bad. That's just very, very bad. So let me give a gross oversimplification of CVE 3094, which is not the xz-utils backdoor. So if you log into SSH, right, in 3 lines of code, I've simplified SSH login. You give it a username and a key, and it's going to try to authenticate to see if that is a valid key for this user. So normally, under normal circumstances, SSH is going to check your authorized keys file for whatever user this is, right? What happened here is that iFunc'd loaded a backdoor. So, and this is not exactly the function that was overwritten, but this is like the best simplification I could get to fit on a single slide. So the backdoor here, what it will do is it sort of always would, or the iFunc'd would always return the backdoor. So the normal authentication logic got supplanted by something that the attacker controlled, something that the attacker had inserted surreptitiously into xz-utils. So, which is also why this only worked on x86, because the backdoor payload itself was just like a single x86 slug. So anyways, okay, so the backdoor, it runs the normal code if it is not presented with the attacker's private key. So it checks, there's an embedded public key, and it will check that first, and if that doesn't work, then it resumes normal behavior. That's crazy, because then this person was about to, because this commit landed in xz-utils. This was about to roll out in Fedora and Debian. So we could have seen a situation where one entity had compromised like all of those SSH systems. Like that would have been a big fucking deal, right? So the attack was not actually this simple. This is slideware, but this gives you a flavor of what's happened, right? Like an important function was supplanted by a function that the user controlled. This is only possible because we have this weird linker behavior that's only on Linux. So like real operating systems don't have this. Yes.
Is that correct? Because
no, none of this is correct. This is, yeah.
But I'm saying let's compare this to the SolarWinds. SolarWinds hack didn't rely on this, but it was a very simple sort of hack. They inserted something that was obfuscated, right? So can we really blame iFunc'd, or is it just the complexity of code allowed something like this to?
Right. So the SolarWinds attack modified something at build time, right? And so this is sort of like delayed after that. So like so when SolarWinds starts up, like what you get on disk is what you get in the binary, right? That's why this is a little bit different, because it's like SSH wasn't attacked, right? A dependency of SSH wasn't attacked. A dependency of a dependency of SSH was attacked. So SolarWinds, like the build systems, like the it's Team City in SolarWinds case, like their build infrastructure was attacked. So this is a lot more distant, because like the pipeline for SSH was not really what was affected. So it's like, yeah, it's similar in spirit. It's a supply chain attack for sure. We'll talk about that in a second. But like, I see this as much more insidious, because like it's more of like I can perform the attack and still be very far removed from the thing that I'm affecting, which just makes it's like, and which is why, right? Like xz-utils had no attention on it, whereas SSH would have had a lot of attention on it, right? So, and that's why I think iFunc'd is dangerous, is because it allows you to like attack things that are so far away from your actual target. Do you feel persuaded?
I feel a little bit persuaded.
Okay, that's all I need.
Yeah.
That's probably all I can do. Yeah. Okay. All right. Well, come on. Just believe what I'm saying. Don't ask questions. Don't think critically about this. Maybe I am. Maybe I'm not. Go ahead.
So, question is, so it's a dependency of a major system. So one, I'm not actually sure how much attention it gets in the internet, but so it's a key. How was the key actually not noticed being slipped?
So I don't know, because that's like, there's tons of write-ups about that. There was like, they put it in, so xz-utils does compression. So there's like in the xz-utils test suite, there's a bunch of like expected compression results or something. So there's binary blobs in the xz-utils test suite anyways. Somehow like one of the test files was modified and that contained the slug. And then there was like some weird things. So their build system is GNU IFUNC, uses the M4 macro language. It's super subtle. So there was something that nobody noticed in the macro system that caused, like when you compile it, caused it to like bring in text segments from this, what otherwise would have looked like just like a test binary file. I have not looked into that. That's very subtle in its own right, but like that's using documented features from known tools, right? Is M4 a little obscure? Yes, but like everybody in the world uses auto tools except the CMake people, but like that is a widely used, widely understood thing, right? iFunc'd, the reason I'm pointing out iFunc'd is because like everybody uses GCC, nobody's heard of iFunc'd, right? I think this is the obscure piece. Like this is the thing that nobody even knew we needed to defend against. So that's why I want to put pressure on it, because I think for all the other components of the attack, this was the piece that it's like this is the piece that I think the write-ups, like all the ink that's been spilled on the internet about this, no one has called this out because I don't think anyone understood it was a thing that could receive criticism, right? It's like, nobody knows what the hell it is. I'll get you. We'll keep working on this. I'm gonna convince Andy one day.
I'm saying, you know, I get what you're saying. What's running memory is not, necessarily compiled. And I'm sure that makes testing a lot more difficult, making sure you're checking testing in these cases. I'm trying to understand, like, is that more insidious than just a straight modification? Or is the difference just the complexity?
So
I think they could have inserted a backdoor in a program without iFunc'd.
right. Yes. And people do that all the time. Right.
So is the difference just like iFunc'd is just like another level of complexity to test and arguments?
So I think it's more like, I see it as like iFunc'd is an unnecessary vector for that, right? So it's like yeah, it is. Well, okay, so I didn't do a performance analysis for this presentation. I've got one on my blog post about this. It is not faster than doing other techniques like function, right? Like it's very easy. Start the program up in main, detect the CPU features, assign appropriate function pointers, be like, oh, okay, they've got these facilities, so these functions, I'm going to use the AVX version of them. You can store those in a memory page that's just function pointers marked as read-only. Like you can do this yourself. It's more legwork. You can also like, here's another thing. It's elegant or whatever. Nobody fucking uses this. Like find open source software other than glibc that uses this. I couldn't. I think this feature exists in the compiler and the linker just to benefit the C library, which is all great and wonderful, but like it puts everybody else at risk in a way that is, I think, difficult to understand and protect against. So maybe it's not more insidious, but to me, it's like it's just an unnecessary weakness.
One of the things that sort of thrown in to get away from pre-processing and compiling.
It's not exactly that, right? Because like you could do this with preprocessor directives. But then you've got to have a different glibc for every sub-architecture, right? And so, yeah, again, really not a problem in real life. I think where it came in, because the guy who developed this is one of the guys that first started, so there's the like boot.lin or whatever, like one of the first, like, wasn't even a Linux distro, but one of the first like bootable, like you could download floppy images and then boot Linux, right? So that's the guy who developed this. And so my guess, and I had a very short email exchange with him, and he was like, yeah, I think it was something to do about like, optimizing string functions. I think where his mind was like the glibc that's running in a system, not an installed system, but on the live installer system, perhaps, right? Like you don't know your sub-architecture at that point. So that's where I guess his mind was, but he also said in his email, he's like, I don't really remember. So we have this compiler feature that was used in an exploit that almost took over the planet, and the guy who developed it doesn't really remember why he wrote it, right?
You're associating his name with this hack.
Well, no. I did not press him on that. I'm sure he was wondering, but
to be clear, you said that you didn't see any open source other than the C.
Yes.
But XZ was using.
XZ was, right? And so that's what set it apart. But XZ, the commit in XZ, so if you go and read about this, it's going to say, oh, the malware for xz-utils was introduced in this commit. And that's where that test data was modified to include the malicious payload. I think really, that's not exactly right. So like about a year prior, it was modified to use by Giatan, right? So the culprit GitHub account, same person, right? So then it was modified to use XZ, to use iFunc'd, but it's like, it was a totally like, that should have been an alarm, like, hey, this is a weird, where's the precedent for using this feature to solve a problem like this? And also like, there's no noticeable performance improvement, right? It's like the iFunc'd decides between like two things that are both like, it was AVX2 and like SSE 4.2 or something, basically two like sub-architectures that are on everything now, because it's not like they picked a new, like a Xeon only function and tried to optimize for that. It's like you're trying to detect at runtime a feature that's on every x86 CPU that's been made in the last 20 years. Like that should have been part of the giveaway.
So the XZ library is pulled into the binary. Why does the test case matter at that?
The test case, right? So it's because, well, it was.
Yeah, why is the test case being run outside of like?
It's not. It was the build system, and so this is like, I don't cover this at all because I'm not going to give you a good explanation, but you can look this up because other people have done a good job with this. The build system, because at build time, the test data is available. So it just like, there's a sneakeroo in the build script to like grab.
Okay.
Yeah. So
actually an exploit at build time.
Sort of. So that's right. So I see your argument. So it's solar windy in that point, right? Except SolarWinds was an infiltration of the build host.
Yeah, but I'm just trying to understand.
Yeah.
During the build,
yes,
the test was run, the iFunc'd was triggered.
No, not even the test, not even then. No, yeah. It's not that the test was run, it's the test when the build is running, not when tests are running. When the build is running, the test data happens to be like, that it's on disk because it's in the repository. So the build system just sneaks over and like knows like, okay, these pages in that file are where my payload actually is. So that's where the backdoor function was and the attacker's public key was. So So those were loaded into the binary at compile time. And so like, that's how like, none of this was in source code, except the only thing that they needed to have in source code was something, they needed some way to use iFunc'd, right? Because they needed the linker to run, and this is where we'll get into in a second, the linker, like when you're loading a dynamic library or a dynamic program, normally, what's it do? It goes through and it's like, I'm gonna get all your dynamic libraries, I'm gonna load them into memory for you. iFunc'd is basically a plugin for the dynamic linker. So when the dynamic linker runs, you can give it your own code to run, and it will do arbitrary logic at link time. It's fucking crazy, right? Yeah, that's the problem. So that's why I think this is a problem.
Just
yes.
to clarify, this is taking advantage of a feature that went in 30 years ago?
Yeah, 20 for sure, yeah. But yeah, it's ancient.
I'm thinking back to the Slackware days.
20's not.
Well, it's, okay, no, that's very fair. That's, hey, listen. No. I've got my file server at home is running Open Solaris. I get it. 20's not ancient. Okay, so any other questions on this slide? We got to get moving, people. We're not going to be able to drink tonight. Okay. All right, so how did iFunc'd get into SSH? I may have covered this a little bit in that discussion, but we'll see it again. So this is where we get to what Andy brought up, likening this to SolarWinds. This is what we call a software supply chain attack. If you've been talking about SBOMs in your work lately, that's part of the concern here. Although this would have gotten around an SBOM, but whatever. So where do we get SSH for Linux, right? That's not its own thing. That comes from somewhere. It comes from a project called Portable SSH, which ultimately comes from OpenBSD. The OpenBSD people are the people who make SSH. They do not give a fuck about Linux. They don't like Linux. They don't like Linus Torvalds. They will go out of their way, like all those people probably use Linux in their day jobs because no one's paying anyone to work on OpenBSD. But like when they are sitting down to like write software, they want to put on their like Linux haters hat and be like, no, we're doing our thing for our purposes. So there's a lot of OpenBSD specific shit in there that like doesn't exist in the Linux kernel, isn't in GNU libc. So Portable OpenSSH strips out the OpenBSD specifics and they make it more POSIX-y, and then people take that and they make it more Linux-y. So this is where like the systemd tie-ins come in. But also Portable SSH does something else, right? This is how we get SSH on Mac OS and Windows and other platforms. All of those things come from Portable OpenSSH. But that's another small project. That's a one-person outfit, Portable OpenSSH. So this, again, we're talking about like these weak links in our supply chain. The gap between the SSH developers and the SSH users is one dude. So be afraid of that. So back to Linux. Some Linux distros use systemd, some don't. So we're just focusing on the systemd ones. Systemd has depended on xz-utils for a long time. That's not weird. That's not part of the attack. That's normal, we think. So by modifying SSH to depend on systemd so that systemd is aware of SSH's restarts, then now we get a binary that is different than what the OpenBSD people designed. Their init system is a bunch of shell scripts, right? It's the old RC init system. So to them, the idea that you would need to link against the init system is just not something that they would plan for. So we are already outside of the design criteria for our secure shell server, right? So this already is kind of weird. We also get xz-utils in the address space because of this. And then as soon as we get this commit that brings iFunc'd into xz-utils, we start to get this trigger down, right? And so now we have got GNU IFUNC. iFunc'd doesn't exist on OpenBSD, right? Systemd doesn't exist on OpenBSD. So we've got this weird, and the linker, right? The GNU linker doesn't exist on OpenBSD. They do use GCC, but they've got their own linkers. So there's a lot of technology here now that is going to affect how OpenSSH resides in memory, and the designers of OpenSSH are not even aware of any of this. So this is dangerous. Do you have a question? No, okay. You can have a question, Daniel, it's okay. All right. Okay, so this is what led to the SSH backdoor. So we got Stallman again. We will keep getting Stallman. It's not going to go away. How does iFunc'd work? There's a lot going on here. We need to talk about dynamic loading. We're going to have a quick lesson on that. It's super complicated. I thought you just start up a program and it loads its dynamic libraries. There's so much more going on. But actually, what we're going to do first is look at static loading because it's easier to understand, and then we'll build up to dynamic loading. So when you start a static program, so this is a program that links against no libraries, not even libc. The kernel loads it into memory. It comes in two sections. There's more, but we're going to focus on two. There's a data section that's got constants, global static variables, whatever. And then there's the text section, which has got all your code, right? So these are sort of your two main components of a static binary. When you start doing dynamic binaries, there's more sections. There's also code that sort of the loader will like selectively include in your address space, but this is what it looks like in the simplest possible case. And the text section is marked read-only, right? Because in a static binary, we don't need to modify it after we launch. So we can mark it read-only, and this way, when you've got a buffer overflow, and someone's like, oh, I'm going to write into your address space, the kernel's like, nope, that memory page is not modifiable. Attempts to write to it causes a segfault. So you will get a crash instead of malware. That's what you want. That's a good failure case. Okay, so now dynamic loading 1. Libraries get loaded into your program at runtime. The kernel, when you start a dynamic program, you're not actually starting the program, you're starting a tool called ld.so, and that acts as an interpreter. So that's kind of neat. It's like when you have a shebang at the top of a shell script, right? You're calling the interpreter. ld.so is an interpreter for all of your dynamic programs. It's going to look at your dynamic program and figure out what shared libraries need to be loaded. And then it's going to look at those libraries and figure out what their dynamic dependencies are, right? So it keeps resolving this until it's got like the full sort of tree structure worked out. You can use a program called LDD to see which libraries a program needs. So there's like Python 3 needs libm, which is your math library, libc, which is a different compression library, expat's your XML library, so on and so forth. So what LDD will tell you is on the left, it's like, here's the libraries I need. And then on the right, it's like, based on the current system configuration, here's the path to where I expect those, like, unless you give it other environment variables or flags, those are the places where LDD is going to try to find those libraries. And if you get a question mark, that means LDD doesn't know where to find something, they won't be able to launch your executable. Okay, so it's still more complicated than that. In the original case, right, in the case that I was just describing, the libraries don't actually get loaded until you first make a function call to them. So like, if you don't do any trig until later in your program, your math library is not actually going to get loaded off of disk until later in your program, right? So you could get into a case where like, there's two issues there. First off, your program text remains modifiable at runtime, right? So that's bad from a security perspective. Also, you could start a program, delete a dynamic library, and then run a function that it needs in the program would crash, right? Which is like, doesn't really happen that often. It's kind of a weird failure case. The new thing that everybody's doing is called railroad. This is relocation at runtime, relocation read-only. I can't remember what the acronym is. All your dynamic functions get resolved before main. So instead of waiting until the first function call, the loader looks through everything and it's like, okay, you're going to need all these different dynamic functions. I'm going to resolve them right now before I go into main. So this is good because then it can mark the text read-only. So that's good. So these decisions are made, and then we've got these read-only pages. And so by the time we start main, then you don't have to worry about like getting attacked and somebody going and overwriting those or like hijacking control of your program. So that's pretty slick, except iFunc'd undermines that because it lets you run arbitrary code during the link phase. So the idea behind railroad is that like all these decisions are made before an attacker would have any opportunity to control program logic. But because iFunc'd, those functions I showed you earlier about like, oh, if it's Tuesday, I want to do this. If AVX is available, I want to do that. Those are functions. You can do whatever in them, right? Like there's no restriction on what can be done. If you call other dynamic functions in other libraries, they will get resolved for you. Like that is arbitrary code that can be run at that point. So yeah, this includes overriding previously loaded functions. And because this is running before railroad finishes, your program text is still writable, right? So like your arbitrary code can include things like going and tampering whatever other functions you want to. And that is fundamentally how xz-utils worked, right? They took advantage of the fact that they had control over the link phase. That wouldn't have happened on a non-GNU platform. That wouldn't have happened anywhere we didn't have the GNU loader. And so that's how they were able to inject their backdoor. Not just inject their backdoor, but like modify, like make their backdoor be resolved, control how that function was resolved. They should not have been able to have control over function resolution, is my opinion, and also correct. So like go-to, I think we should consider iFunc'd harmful. All the focus is on social engineering, but I'm like, the linker did the social engineer, right? The linker social engineered all of us. Like this wasn't the one dude that was the xz-utils maintainer. This was us not knowing that such a thing could even happen. Most software does not need this. All Linux software is vulnerable in the sense that like if any library that you need to use has had this done to it, you can't stop it from happening, right? Like you can't stop if you got a program that's mission critical for you, and it depends on something that's been contaminated. You cannot stop them from abusing iFunc'd to modify your function table before main starts. Like you cannot stop this with the GNU loader. I think this should not be enabled by default. glibc needs it. There needs to be some compromise worked out there. I don't know what that compromise should be, but like I should not have to be vulnerable to this by default. What can we do? I don't know. Like this just exists. We can raise awareness. I think making memes is a good way to raise awareness. If you can figure out what parts of your stack use iFunc'd, basically it's going to be glibc and then probably nothing else, right? But like, I don't know that. I looked pretty hard to find open source software that used it. Just because I couldn't find it doesn't mean it doesn't exist, right? If you can find something, it could be worth, like, we're not developers here necessarily, right? But like, we depend on other people to give us software that isn't going to cause a shit show for our work. So if you find something, like maybe you can agitate the maintainers, be like, hey, can you explain why you really need this versus, doing this at, doing preprocessor directives, building multiple binaries, using function pointers. There's like 10 different ways to do this, right? Like, why do you need a linker plugin to do this? They may have a good answer, but it's worth asking for. Also, again, if we stop using computers, problem goes away. That's all I got. Is anybody not sold on that? Can I take a moment to sell you on this? I want to start pounding nails into the iFunc'd coffin. So if anybody's willing to like dig it up and revive it, I want to demotivate you on that front.
Should have brought some pop.
I didn't think of that until just now, though.
So, earlier, a lot of military security compliance. When I look at this little scenario, what I see is a very slowly played and who's behind this? This was not an accident. This is something that was put out on 3-year, 5-year timeline where
And hard to do that one at a time. We put a lot of work into this. Really clever.
Super close.
Me and Microsoft got found.
Yes, yes, yes.
Very scary slow play.
Yes, and I think and this is why, to me, I felt it was important to raise awareness about iFunc'd, because there was so much focused on like, this one maintainer was, this like there's just one guy maintaining xz-utils. I'm like, that's important. That's a problem in its own right. But we've got a lot of software where there's just 1 or 2 people maintaining it, right? But like iFunc'd is like, it's part of GCC. That is not a one-person operation by any stretch. And I go ahead.
So fact that this is now part of it, dependency. Because I remember having all the student flags in GCC. And so I get the fact that you should have, like, you know,
So,
but this sounds like a very deliberate, slow way.
and people don't know, so there's a lot of hypothesizing, right? It's like, yeah, it's like, oh, this had to be a nation state. It's so complicated. I think that by the time you understand iFunc'd, this attack becomes obvious. So maybe it was a nation state. I don't know. It's certainly, you see actions taken over a period of a few years, but I'm like, I feel like a person could have done this. Like, it is just like, once you understand that you can write plugins for other people's linkers, what would stop you from drawing the rest of the horse, as we say, right? Like, I think this is.
It's drawing the rest of the
Okay. Thanks, Wesley. So the horse is the wrong animal there. Okay.
I think it's discovered.
Oh, yeah. So this is great. So Microsoft, I think Andy just mentioned this, a Microsoft engineer who's a great guy. I showed Flash Gordon earlier, but I showed Flash. He was doing performance testing on Postgres. And yeah, here's a picture of him. So this is Andres Freund. And he was doing performance testing, and he noticed at some point, there's some part of his workload that logged in through SSH to do some part of the performance testing, and Postgres performance testing. So I guess this guy's just like performance mindset or something, but he was using this because he was using bleeding edge. I don't know if it was Fedora or Debian. Noticed like, man, my SSH sessions are taking a lot longer to connect. So he started debugging that because he had time on his hands. I don't know. But this guy was like, let me go down this rabbit hole that is unrelated to my day job. And because he did that, he started doing dynamic tracing. I gave a dtrace presentation several years ago. But he used some, it was Linux, so I guess he was using BPF trace, but like started noticing like, wow, I'm profiling this and we're spending a lot of time in, this one function that does, that evaluates some part of RSA, right? So that's where like my slideware earlier was a little oversimplified. It's not the whole like key checking thing. It's just part of what's needed to check RSA keys. And that is like normally should be pulled in from OpenSSL, but instead of being pulled in from OpenSSL, it was pulled in from the payload that was slipped into the testing, right? So that's normally should have taken so many CPU cycles, but was taking a lot more because there was I don't know, it was slow. Like the malware wasn't designed by somebody that knew how to make it performant. So I don't know what was wrong with it, but
Why would they?
why would they?
Who
Yes.
would have expected that to be the way
It, yeah. Right. No. Yeah. Yeah. So, but yeah, that's what it was. Somebody was noticing that it took slightly longer to log into SSH than usual, and they took the time to debug it before everybody started adopting that rolling release of their distro. And, I mean, like we were days away from this. So
that you've been able to track it back to a commit.
So yeah, it's tracked back to commits. And so there's three commits in question. The malware was introduced in 2 commits earlier this year. So in like February, I think this was all discovered like beginning of March. So like or maybe it was end of March. Sometime in March, this was discovered. So the commits were made about a month before that, and then things started rolling out. Things started, like we're going to pull an xz-utils, package it. We're like cutting our bleeding edge, whatever. Like this is our release candidate. So the commits were introduced before that, and there was like to hide them. One was like, okay, I'm updating the test data, and another one was I'm going to make a very subtle change to the build system that would eval some other script and like let me pull in this test data and inject it at build time. So to disguise those are 2 different commits, and that's what everybody's focusing on. And what I want to complain about is like a year prior, a function was needlessly changed to use iFunc'd. Because I think they did that. They had this whole thing planned out, did that first, and then waited before introducing this paper.
And all those commits were from the same person.
All those commits were from the same person, right? Yeah. Everybody convinced? iFunc'd bad, thumbs down. Okay, all right, yeah, okay.
I'll tell you what, sold me was the idea of just turning it off by default. Okay, that makes perfect sense.
Yeah. Well, the trouble is then you can't load glibc. So,
Okay, so here's the other thing. Why have dynamic loading at all?
and listen, did you see my, hold on.
Well, we just face it. Right?
And it's to save RAM, and RAM's getting cheaper by the day, right? All shared libraries must die.
Yeah.
Well, I mean, this, it's super complicated. There's attack surface now. I think this is something that, like, I never in my life considered that dynamic libraries would be attack surface, right? So, like, now that it is, I personally would much rather waste the RAM to defend myself. Like, I can spend the money, like, do I need to buy more RAM as a defense mechanism? Yeah, that's a solvable problem. I can spend that money. Also, the complexity of loading goes way down. Like, why the hell not? Also, just from I used to install software on supercomputers, and managing packages, being a human package manager is like a miserable ordeal. If you can not have to do that, I mean, that's not a big crowd, right? But like, that would have made that part of my job a lot easier.
Yeah,
So
I would just say, like, ancient system, you lose your partition. You lose all your shared libraries and you are SOL.
So one thing that, it does make shared libraries make fork and exec faster, because the kernel knows that these things already exist in memory. And when you go to load them, it can be like, I'm just going to remap these pages for you. So it's not just space savings. There is also some performance savings. And that matters if your workload is like a bunch of shell scripts that are always forking and execing things. If your workload is like one program that's just running in memory, you don't give a shit. So,
you want every little click to go.
Yeah, but supercomputers aren't forking and execing though. They're startup. They're good. They also
Libraries are one of that code as clean as they can.
No more shell
no more what?
scripts.
Not for Euro. Yeah, that's yeah. I'm not going there, Caleb. I'm not going there. Did you finish that game ever? All right. Okay, that's all I got. Can I get back to, can I make one more point before we go about open source? I don't know how I left this out. Where's my, okay. Here's the, this is, so what Caleb just said, he was talking about his game. He was like, oh, it's open source. You can fork it. You can do what you want with it, right? That is the ethos of open source. Like, I can solve my needs with your software without having to bother you about it, right? Like, I can take your ideas and go do my own shit with it. And that's what's happened with SSH. The OpenBSD people make it for their needs. The Linux people have, through a pipeline, have sort of modified it for their needs for system compatibility. And then xz-utils, so you've got sort of these three components. Like, xz-utils is not working its security apparatus to defend against attacks on SSH, right? And the SSH people are not designing it so that it will have these weird, to be secure in an environment where you can have like loader plugins, because they don't have that. So it's like, you've got this thing of the left hand not knowing what the right hand is doing. And that, I think, is like a big pitfall of open source. Whereas if you look at, like Solaris, right? Like, Sun had their own SSH. Sun had their own compiler. Were those any good? Maybe not. But you've got like all of these pieces are designed under one roof. And so you get different problems with that. But one of the problems that you're not going to get is like this type of shit that can happen like a patchwork ecosystem.
Oh, I mean, not having worked in large, I strongly disagree.
Okay. Well, okay. So that's fair, right? It's like, do the people on the third floor not talk to the people on the second floor? Like, that can happen.
And the other thing is, like, I think, again, if you contrast this with solar, like, nobody can use that. Nobody, I mean, maybe a handful of people inside who viewed it, profiled it. They went out. It went into government agencies. Like, that was successful.
Yeah, but that was smaller too. So,
No, I mean,
oh yeah, that was way smaller.
the potential radius for this was much larger.
Yeah.
But it never went out,
Well, okay.
you know?
All right. It was close, man. Yeah, but you're down to one dude. Like what if he was sick that day?
I know.
That's like-
I know.
I feel like that was close enough that we shouldn't disregard this as like this didn't go out. Like I think that's like
That's fair.
we should all consider that we won the lottery here.
So,
Why have we not caught this one?
Fortunately, nobody uses iFunc'd, so I think we're okay. But it still would be good if it could be constrained somehow, because like you can't get away from it. Like if you are using the GNU loader, this is a thing that can happen to you. And
You had a lot of really cool guys that's around pick up this stuff, and suddenly Iranian centrifuges stop over here, go off the rails, and we don't fly. Right.
the Iranians should get their own loader. Yeah.
Got out of the lab virus.
Okay, I've lost interest in this subject, so we should move.
Great job.
Go to the water goals around town, so stick around and join us. And thank you very, very much. We have a lot, yes, we have a lot of pizza, and some of it can go Turkey Creek, but I mean, I'm sure there is a low limit where you guys will carry, right? So we need some takers to take these home with them, and I know like there's at least 2 takers. I'm convinced, so please do, go up there and inspect it, don't be shy, take it.
I'm glad you
you.
came out. I really am.
Yeah.
Thank you for having me.
Thank you. You know what?
Yeah.
Yes, and thank you very much. Aaron, thanks to you.
Oh, thank you very much. This represents